I'm going to talk about our exciting studies that reviews where the host network stack spans CPU cycles and where the main overheads come from. Let's start by looking at the network and host hardware trends that motivate our work. For the internet and early generation data center networks, the network core was the primary bottleneck. This is because a single CPU core can easily saturate 1 to 10 gigabits, and even with relatively recent optimizations, even 40 gigabits. Hence, the main challenge in early generation networks was to efficiently share network resources like switch buffer and bandwidth. Over the past 2 decades, network and CPU technology trends have been significantly different. In particular, network bandwidth has increased by 100x, thus require much more CPU resource for packet processing. However, slowdowns of Moore's law has resulted in per-core CPU performance and per-server CPU capacity being largely stagnant. This has led to performance bottleneck, shifting from the network core to host network stacks. A single core can no longer saturate the entire existing bandwidth. And the challenge now is to efficiently share host resources, such as CPU core, DRAM bandwidth, and L3 capacity. To address this new challenge, the community has been exploring a variety of potential solutions, including Linux kernel stack optimizations, RDMA, hardware offloads, and user space stats. The design space explored by all these potential solutions will benefit from a detailed understanding of today's network stack overheads. Building such an understanding is a goal of our work. Before diving deeper into our results, let's briefly summarize our experimental setup and methodology. Our goal is to understand CPU overheads of the Linux kernel network stack. To ensure that our setup indeed pushed the performance bottleneck to the host network stack, we use 2 servers connected directly over a 100 gigabits link. We are interested in understanding throughput, CPU utilization, and CPU utilization breakdown. We also measure low-level system metrics like cache miss rate to provide insights on our evaluation results. We evaluate the impact of various factors, starting with various optimization techniques like TSO-GIO, jumbo frames, and ARFS. TSO and GIO are the well-known offload techniques for splitting and coalescing data, respectively. Jumbo frame use 9,000 bytes MTU size. Lastly, ARFS steals the incoming packets to the core where the corresponding application is running, so that the cache performance can be improved. We also consider different hardware configurations, namely DDIO, which is enabled by default on our servers, and that allows the NIC to directly DMA packets to the L3 cache, and the IOMMU, which allows creating per-device virtual address space. Further, we consider different traffic patterns and different flow size, including long flows, as well as a mixture of long and short flows. Finally, we also evaluate the impact of packet drops and congestion control protocols. I'm sure the audience here is familiar with the Linux network stack data path, but for the purpose of the completeness, let me quickly go through it. Application first initiates a write system call to send data. It copies the data from the user space to the kernel space and performs context switching to the kernel mode. The socket intercepts the data and transfers it into a packet or SKB and put the packet into the socket write queue. When ready to be transmitted, for example, congestion control window or rate limits permitting, the data is passed from TCP IP layer to the driver, and driver creates a necessary mapping for the NIC to DMA packets. As packets reach to NIC, if TSO is enabled, NIC will segment the packets into multiple MTU size packets. NIC will eventually transmit those packets to the receiver side. When AIFS is enabled, the packet will be forwarded to the receive queue corresponding to the application core. Otherwise, the packet may be forwarded to the core chosen based on the 5 tuple. The receiver NIC DMs the packet into the NIC ring buffer and triggers IRQ to notify the driver. After receiving the IRQ, the driver starts to pour packets in the ring buffer and pass to GRO layer. GRO aggregates these packets from the same flow into a big chunk of a packet and then send to the TCP IP layer. TCP IP layer pushes the packet into the socket read queue and wake up the application thread to copy packets to the user space buffer. Our study resulted in several interesting takeaways which depart from conventional wisdom. First, data copy is the primary bottleneck, which with over 50% of all CPU cycles at the receiver spent in data copy. Second, the rapid increase in access link bandwidth have led to the NIC DMA pipeline becoming inefficient. For example, a large part of the data copy overheads come from significant increase in cache miss rate during data copy. This is because during the DMA process, NIC overrides data in the cache before the application is able to read it. Third, multiple flows sharing host resource didn't have any performance implication in the internet or in early generation data centers, since bottlenecks were in the network core. However, this is no longer the case. We see sharp degradation in throughput core, with increase in the number of the flows sharing host resource. Lastly, it turns out the short and long flows have different performance bottlenecks, which make it hard to efficiently orchestrate host resource when these flows are co-located. We see 40% super drop for both short and long flow when co-locating them. In the rest of the talk, I will walk you through each of these takeaways one by one and provide intuition and evidence for these observations. We start by looking at the performance of a single long flow. While this seemingly simple scenario was not interesting for low bandwidth networks, in the context of high bandwidth networks, it already provides several new insights. Until 40 gigabits, a single core could saturate the entire access link bandwidth. However, we find that multiple cores are needed to saturate 100 gigabits. We successfully turn on optimization and see their effect on throughput code. Place like here means there is no software and hardware optimizations are enabled. Here, throughput code is only 4 gigabits. Looking at the corresponding CPU breakdown on the right, we see that the TCP layers takes up the majority of the CPU cycle. This is because the TCP layer has to process MTU size packet, so per packet overhead is high. After enabling TSO-GRO, throughput core increased to 15 gigabits. We see that the TCP IP and locking overhead are reduced. As the network stack now operates on larger 64 kilobyte packets, since GRO will coalesce packets before TCP processing. The net device layer is responsible for several low-level packet processing functions. This is where GIO is implemented, and hence we see a corresponding increase in that overheads. Enabling 9,000 bytes jumbo frames further improves throughput per core to 27 gigabits. As we can see, it reduced GIO overheads as MTU is now larger and the bottleneck shifts to data copy. After enabling AFS, throughput per core reached to 42 gigabits. Enabling AFS co-locates the interrupt processing on the application core, which leads to better cache locality. This improves data copy efficiency and also reduces overheads of a memory and SKB management. Seeing as the data copy takes more than 50% of total CPU cycles, we need a better mechanism for reducing data copy overheads. Zero copy techniques like TCP AMAP and XDP can alleviate this bottleneck. However, they both require significant application logic changes, and the latter requires implementing the network stack in user space. If we can realize an efficient zero copy mechanisms, it may be possible for a single core to saturate the 100 gigabits links. Next, let's discuss how the NIC DMA pipeline has become inefficient. We found high cache miss rate is a core reason for the inefficiency of NIC DMA pipeline. And there are two parameters that impact the cache miss rate: NIC X buffer size and the TCP X buffer size and NIC X descriptor size. Let me first go through the first parameters. In the graph, we observe that as we increase the TCP X buffer size, throughput decreased due to high cache miss rate. This is because larger TCP buffer size increased the amount of in-flight data, hence increasing the packet processing latency at the host. We measure this latency in Linux and confirm that this indeed happens. To understand the impact of this, let's look at the figure on the right. Say some packets arrives at the NIC. The NIC will transfer these packets to the L3 until the L3 capacity used by the DDIO is completely utilized. If packet processing latency at the host was low, the application would promptly copy these packets from the kernel buffer to the application buffer from the L3. However, since the packet processing latency is high, by the time the copy starts, the NIC already overrides packet in the cache. As a result, data copy experience high cache miss rate and the overall throughput per core reduce. The second parameter is the number of NIC IX descriptors. This is the number of the frames that a NIC can DMA packets before they need to be replenished by the driver in software. We find that as we increase the number of IX descriptors, the cache miss rate increase and the throughput reduce. Even in the case when the TCP buffers are small and the amount of in-flight data would fit in the L3 cache, we still see this phenomenon. In this case, even the L3 capacity for DDIO is not full. The second packet evicts the first packet from the L3 and leads to cache miss when the data copy performs. We hypothesize this is due to a suboptimal cache replacement policy that precludes the usage of the entire L3 cache. We do admit we need a deeper understanding of this phenomenon to address it. However, the number of descriptors should be chosen carefully. And we also found out when enabling IOMU, the throughput per core further drops by 26%. Looking at receiver side CPU breakdown, we find out memory allocation and deallocation becoming more prominent in CPU consumption. Now, it consumes 30% of total CPU cycles. This is because of 2 additional per-page operations required by LMMU. When the NIC driver allocates new page for DMA, it has to also insert this page into the device page table or domain on the LMMU. Once DMA is done, the driver also has to unmap those pages. These 2 additional per-page operations result in increased overheads. Another reason of the degradation may relate to the mismatch between the number of IOTLB entries and TCP window size. In high bandwidth network, the number of in-flight data may be greater than the size of IOTLB entries, hence increasing the miss rate of IOTLB and causing the super drop. The degradation may be worse when the receiver receives more than 1 flows. More analyses related to the IOMLU will be covered in our future works. The above results suggest that in addition to classical parameters like bandwidth and runtime time delays, transport protocols or read control or window size calculations should take host resource like L3 capacity, host packet processing latency, and even IOTLB entries, the number of IOTLB entries, into account. Another possible solution is to reduce host packet processing latency by parallelizing data copy dynamically across multiple cores. This can be achieved by decoupling data copy and packet processing, but will require re-architecting the network stack. Also, we need a better cache replacement policy for using the cache resource more efficiently. Next, let's discuss how host resource sharing degrades the performance. In the incast, where a number of sender cores are sending data to a single receiver core, all flows are sharing receiver core resource, most notable the caches, which leads to cache contention and subsequently poor performance. In this graph, when we increase the number of flows, the super per core reduce and the cache miss rate increase. It suggests that the need for careful orchestration of host resource among the contending flows. Such an orchestration is hard with TCP given its sender-driven nature, since receivers have no control on when and how many senders can send data to them. It is hard for them to efficiently share receiver resource across flows from different senders. Recent works on receiving-driven transfer protocols like phost, NDP, and HOMA could enable such an orchestration. Next, we look at the case of all-to-all, where there is a flow between each sender and the receiver core pair. Here, in addition to contention for cache and CPU, the network link bandwidth becomes a new bottleneck. We find that this further degrades super per core as the number of flows increase. This can be explained by the following. Looking at the receiver side CPU breakdown, we find that scheduling overhead increase with more flows. This is because each flow receives a small share of the link bandwidth, causing application to go to sleep and wake up repeatedly while waiting for packets. We also find that packet aggregation techniques like GIO become less effective when more flows contends for the host resource. For the graph below, we plot the histogram of SKB size received by the TCP IP layer after GIO. we can see that as we increase the number of flows per core, GIO efficiency reduces. This is because lower per flow bandwidth result in reduced opportunity for coalescing packets. To resolve this contention, again, we can use receiving-driven transfer protocol to orchestrate receiverless bandwidth. More generally, we believe that designing transfer protocols for high bandwidth networks requires solutions that encompass techniques from not only computer networking, but also computer architecture and operating systems. Finally, let's discuss how co-locating short and long flows degrades the performance. We see a super core degrades when co-locating long and short flows. Typically, the overall super core reduced by 47%, while long flow degrades 48% and short flow degrades 42%. Diving deeper into the results, we compare performance characteristics of short flows with long flows. We find long and short flows have different bottlenecks. Firstly, we look at the CPU utilization breakdown for both and long and short flows. Immediately, we see the performance bottlenecks are very different. TCP and the scheduling overhead increase as we decrease the flow size. We also find out the data copy overhead contribute less in short flows, which potentially means DDIO won't improve the performance of short flows as long flows. As we can see, to tackle the difference in bottlenecks, we must have dedicated packet processing pipelines for both short and long flows. We also need to design an application and a network-aware CPU schedulers to schedule long and short flows on different cores. In summary, our study has 4 key takeaways. First, data copy is the primary bottleneck for high-speed networks, and we need to design effective zero-copy mechanisms to alleviate this bottleneck. Second, the NIC DMA pipeline has become inefficient. TCP buffer size calculation must take the host resource, like L3 cache, packet processing latency, into account. And we need to rethink the design of the host network stacks as well as host architectures in order to improve the DMA pipeline. Third, host network stacks performance degrades significantly with increase in number of flows contending for host resource. We can use receiving-driven transfer protocols to carefully orchestrate host resource. Lastly, since co-locating short and long flow is harmful, we need an application and a network-aware CPU scheduler to schedule the flows. For a more detailed analysis on even more workloads, please read our paper. All the tools used for profiling and measurements are available on our GitHub repository.